every type of space debris threat, space is complicated. We make it simple. Low Earth orbit is a junkyard, not metaphorically. Literally, physically, right now, there are hundreds of millions of human made fragments circling the planet at speeds fast enough to punch through steel, and almost none of them are tracked closely enough to reliably avoid. Every category on this list is debris humanity put there ourselves, and every category makes the next collision slightly more likely. We're going in order from the smallest, most numerous threat to the largest, most catastrophic one. Then we'll sort them a second way by how solvable each problem actually is. Because some of these we could clean up starting tomorrow, and one of them may already be unstoppable. Paint flecks and micro debris. We begin with the smallest object on this list, and also the one that should bother you the most given how little it takes. Orbital debris in low Earth orbit typically travels at around 28,000 kilometers per hour, and at that speed, kinetic energy scales so dramatically that even a fleck of paint, barely a few millimeters across, carries roughly the same destructive force as a bowling ball thrown by hand. Here's the fact that changes everything about how spacecraft are actually designed. A paint fleck struck one of the space shuttle's windows in 9983 with enough force to gouge a pit large enough that the entire window had to be replaced after the mission from an object smaller than a grain of rice. NASA now tracks tens of thousands of debris objects larger than 10 centimeters, but the population of untracked fragments below that size, down to the millimeter scale, is estimated in the hundreds of millions, each one too small to reliably detect from the ground, and every single one large enough to disable a critical system if it hits the wrong spot. Spacecraft designers now build multi-layer shielding called Whipple shields, specifically designed to shatter and disperse the energy of these tiny high-speed impacts before they can punch straight through a hull, a defense against an enemy too small to see coming. Defunct satellites and rocket bodies. Here's the twist. Some of the largest, most dangerous objects in orbit aren't debris from a collision at all. Their entire machines, fully intact, simply abandoned in place once their mission ended. Thousands of dead satellites and spent rocket upper stages remain in orbit today, some dating back to the earliest years of the space age, still circling the planet decades after their last transmission, too high up for atmospheric drag to pull them back down within any reasonable time frame. Here's the fact that should genuinely bother you. These aren't just clutter. They're some of the largest single objects in orbit, meaning a collision involving one of them doesn't just risk destroying two spacecraft. It risks generating thousands of new fragments in a single event, each one becoming its own independent hazard for decades or centuries afterward. Rocket upper stages carry an additional specific danger: leftover propellant and pressurized tanks that, over years of temperature cycling in orbit, can spontaneously rupture without any external collision at all, an event that has happened dozens of times and single-handedly created some of the largest individual debris clouds ever recorded, entirely from an object, simply sitting there, doing nothing, until it wasn't. Radioactive debris. Here's the fact that adds an entirely different kind of danger to this list, one that doesn't stay in orbit at all. Several nations, most notably the Soviet Union, launched satellites powered by onboard nuclear reactors, primarily for military ocean surveillance purposes during the Cold War, designed to be boosted into a higher, longer-lasting disposal orbit once their mission ended, rather than falling back to Earth. That plan didn't always work. In 1978, the Soviet satellite Cosmos 954 malfunctioned and failed to reach its intended disposal orbit, re-entering Earth's atmosphere uncontrolled and scattering radioactive debris across a remote stretch of northern Canada, triggering a multi-million-dollar joint cleanup operation codenamed Operation Morning Light that searched thousands of square kilometers of frozen wilderness for irradiated fragments. Here's the fact that should genuinely bother you. Cosmos 954 wasn't an isolated incident. Several other nuclear-powered satellites have experienced comparable failures over the decades, and a number of them remain in orbit today in their intended disposal orbits, meaning any future collision or premature decay affecting one of these specific objects carries a category of risk fundamentally different from ordinary metal debris. Not just a physical impact hazard, but a genuine radiological one raining down on whatever happens to be underneath the reentry path at the time, the Kessler Syndrome. Here's the reframe. This is the scenario that turns every category on this list from a nuisance into a potential extinction level problem for orbital spaceflight itself. First proposed by NASA scientist Donald Kessler in 9978, the Kessler syndrome describes a theoretical tipping point where the density of debris in a given orbital region becomes high enough that collisions between existing objects generate new debris faster than atmospheric drag or active cleanup can remove it. A self-sustaining chain reaction where each collision statistically increases the odds of the next one. Here's the fact that should genuinely unsettle you. In the worst case models, certain heavily used orbital bands could become effectively unusable for generations, not because they're physically destroyed, but because the density of high-speed debris makes safely operating a spacecraft there statistically untenable, cutting off humanity's access to specific altitudes that satellites currently depend on for communication, navigation, and weather forecasting. Nobody believes we've crossed that threshold yet. Most orbital debris experts agree we are measurably, uncomfortably closer to it than we were even a decade ago. And the trend line is moving in the wrong direction as more satellites launch every year. Confirmed collision events. Here's the pivot. This isn't purely theoretical. It has already happened more than once, with directly observable consequences still circling the planet today. In February 2009, a defunct Russian military satellite, Cosmos 2251, collided with an active American communications satellite, Iridium 33, in the first confirmed satellite-to-satellite collision in history, an accidental impact that instantly created over 2,000 pieces of trackable debris and untold thousands more too small to individually catalog. Here's the fact that should genuinely bother you. In 2007, China deliberately destroyed one of its own defunct weather satellites with a ground-launched missile as an anti-satellite weapons test, instantly creating over 3,000 pieces of trackable debris in a single controlled demonstration, a significant fraction of which remains in orbit today, over 15 years later, still a hazard to every other spacecraft sharing that altitude. Between these two events alone, thousands of new individually tracked fragments were added to low Earth orbit within a span of just 2 years from a single accident and a single deliberate weapons test, each fragment now capable of triggering the next collision in the exact chain reaction the Kessler Syndrome describes. Anti-satellite weapons testing. Here's the fact that should genuinely bother you more than any accident on this list. Unlike collisions, which happen unpredictably, anti-satellite weapons tests are a deliberate, repeated choice conducted by multiple nations specifically to demonstrate the capability to destroy an adversary's satellites during a potential conflict. The United States, Russia, China, and India have all conducted destructive anti-satellite tests at various points, each one adding a fresh burst of trackable and untrackable debris to orbit, entirely as a byproduct of demonstrating a military capability rather than any accident. Here's the part that lingers. A single destructive anti-satellite test conducted during an actual future conflict, rather than a controlled demonstration, could plausibly generate enough debris to meaningfully accelerate a Kessler Syndrome scenario in the targeted orbital band, meaning the debris consequences of a hypothetical war in orbit could easily outlast the conflict itself by decades, continuing to threaten civilian satellites belonging to every nation on Earth, including ones that had no involvement in the original dispute at all. Megaconstellations and the crowding problem. Here's the fact that reframes this entire category for the present decade. The debris problem isn't only a legacy of the past 60 years of spaceflight, it's actively accelerating right now, driven by an entirely new kind of satellite deployment. Private companies have begun launching megaconstellations, networks of thousands of small satellites intended to provide global internet coverage, dramatically increasing the total number of active objects in low Earth orbit within just a few years, a pace of deployment that dwarfs the entire previous history of spaceflight combined. Here's the fact that should genuinely bother you. These operators report tens of thousands of automated collision avoidance maneuvers annually across their combined fleets, simply to steer around other tracked objects. A volume of near misses that didn't exist as a category of routine operations at all a decade earlier, now treated as a normal, expected part of running a satellite fleet. Proponents argue these satellites are specifically designed to deorbit and burn up reliably at the end of their short operational lives, reducing long term risk compared to older debris. Critics argue that even a small failure rate spread across tens of thousands of satellites could still add meaningfully to the debris population faster than older methods ever did. And given the sheer scale of deployment now underway, nobody will have a confident answer to which argument is right for several more years yet. Active debris removal. Here's the fact that closes this list on its most hopeful note. Humanity isn't purely watching this problem accumulate. Several space agencies and private companies have begun actively testing methods to physically capture and deorbit dead satellites and large debris fragments, using tools ranging from robotic capture arms and nets to harpoons, and even magnetic docking systems designed to grapple with objects that were never built to be captured in the first place. Japan's Astroscale and the European Space Agency's ClearSpace missions represent some of the first dedicated attempts to demonstrate this technology at meaningful scale, targeting specific large, defunct objects for controlled deorbit rather than leaving them to decay naturally over decades or centuries. Here's the fact that should genuinely bother you about the scale of the challenge. Even optimistic projections suggest current active removal technology can only realistically target a handful of large objects per year, a rate that barely keeps pace with new debris generating events, let alone makes meaningful progress reducing the existing catalog population of tens of thousands of tracked fragments already up there. The technology to fix this problem exists in early working form. The funding and the launch cadence required to deploy it at the scale the problem actually demands does not yet exist anywhere close to matching it. The geostationary graveyard orbit. Here's the fact that closes this list by showing how humanity has already quietly tried to solve a version of this problem once before. Geostationary orbit, roughly 36,000 kilometers up, is uniquely valuable because a satellite there stays fixed above the same point on Earth's surface, making it essential for communications and weather satellites. And because that specific orbital band is so valuable and so crowded, operators long ago adopted a voluntary practice of boosting dead satellites a few hundred kilometers higher into a designated graveyard orbit, clearing out the working band rather than leaving retired hardware drifting through it indefinitely. Here's the fact that should genuinely bother you. This system only works if every operator actually follows through with enough remaining fuel to perform the boost, and a meaningful percentage of retired satellites over the decades have failed to reach the graveyard orbit cleanly, either from fuel miscalculation or late life malfunction, leaving them drifting slowly through the same valuable band active satellites still depend on. Here's the part that lingers. The graveyard orbit is proof that humanity is fully capable of managing this problem when the incentive is strong enough. Geostationary orbit remains dramatically cleaner, proportionally, than the crowded chaos of low Earth orbit, simply because operators there had a direct, shared financial interest in keeping their own valuable neighborhood usable. Let's sort these 8 again a different way, not by size, but by how solvable each threat actually is. On the immediately fixable end, confirmed collision events and anti-satellite tests, both entirely a matter of policy and restraint rather than unsolved engineering, nations could simply agree to stop generating debris deliberately, starting immediately if the political will existed. On the actively being solved end, defunct satellites and rocket bodies, a problem active debris removal missions are already beginning to chip away at, however slowly. On the structurally difficult end, microdebris and paint flecks, a threat so small and so numerous that no removal technology currently proposed can meaningfully address it at all. The only real defense remains better shielding on the spacecraft receiving the impacts. On the actively worsening end, Megaconstellations, a problem still being created faster than anyone has fully assessed its long term consequences. And on the potentially irreversible end, the Kessler Syndrome itself, a threshold that, once crossed in a given orbital band, current technology has no proven way to reverse within any human timescale at all. It's worth understanding exactly how debris gets tracked at all, because the entire system protecting every satellite currently in orbit depends on a surprisingly small, surprisingly overstretched global network. Ground based radar and telescope systems, run primarily by military space surveillance networks, continuously scan the sky and maintain a catalog of tens of thousands of objects large enough to detect calculating potential close approaches days in advance, so operators can maneuver out of the way if a collision risk crosses a certain probability threshold. Here's the fact that should genuinely bother you. This entire protective system only works for objects large enough to reliably track, generally down to around 10 centimeters in low Earth orbit, meaning the hundreds of millions of smaller fragments discussed earlier in this video are, functionally, invisible to the exact warning system every operational spacecraft depends on to avoid a collision. They simply can't be individually watched for or dodged, only statistically guarded against with shielding and sheer luck. Here's the last thing worth sitting with. Every satellite currently keeping your phone connected, forecasting tomorrow's weather, and guiding your car's navigation is flying through a debris field that humanity built entirely by accident, one launch at a time, over the past 70 years. And every new object added to it, whether by collision, weapons test, or simple neglect, makes the next accident statistically more likely for everyone flying through that same altitude after it. We didn't inherit this problem. We are right now still actively creating it. Not bad for stick figures on a rock.